handle several terabytes of a database size, right, from the single standpoint. Now, how would that translate in how large applications a single MySQL instance can support, right? And if you do some math and say, well, let's not take those kind of the marketing numbers, 1.5 million plus. Let's take something more conservative, right? Just 100,000 queries a second. What would that give us? And in this case, if you say, hey, you know what, we have our application, right, which has, you know, number of user interactions, and we take maybe 10 queries for each of them, and maybe we are having that gives us so many user interactions a second, right? And looking at some, you know, medium user engagement of maybe, you know, 30 interactions a day, we can still see pretty much of a large number of daily active users, right, from the start. Now, what I mean in this case, and again, your numbers can be substantially different, right? Your transactions can be more complicated. The users may be kind of more engaging with you in a day, right? You may have some other kind of background activities which you say are not counted here. But the point is, what you can really build a pretty serious applications which do not need more than on a single single database out there. Now, even in and another thing which you look at their distributed systems is when you look at the distributed systems wherever they are, they tend to be more complicated to develop against, right? If I'm having a single MySQL system, I wrote the data, it's immediately available. I don't have to deal with anything like a network jitter, which can you know, introduce variable latency or slave lag and so on and so forth, right? Distributed systems also tend to be more complicated to operate or have additional performance bottleneck or additional more complicated failure modes, right? Unlike single MySQL instance, which can be either pretty much up or down, I can have things like slave lagging or replication broke and I didn't notice that, so my data is not updated, right? A lot more complicated. Now, why do I bring those two items together? Because from our side, we see folks trying to go to very complicated architectures very early. And why they're doing that? Because they go to the talks just like this, right? And you would have a lot of people from famous companies like Google, Facebook, Slack, you know, talking about those amazing systems they have built, right? And that gives us an idea, wow, it makes sense to get those kind of a massively sharded MySQL across many kind of data centers. That looks so sexy, that looks so interesting, right? That is absolutely useless for majority of applications out there, right? Majority applications are not Google and Facebook, right, in this case. So that is something which is a very important to recognize, right? And that means a lot of solutions they would talk about would need to be scaled down dramatically to fit for you, right? Again, I do see some faces here already which work with a large scale applications, right? And you can rightfully disagree with me, but still you have to understand that in the grand scheme of things, you are a minority. Okay. Now, with all of those, why do we need to kind of to go distributed, right, and go outside of that kind of single MySQL instance? Well, there are really few reasons here. One is high availability, right? Single instance kind of can easily crash. Scalability, what we spoke about, and also various needs for which require our data to be distributed outside of a single location. Let's talk about the high availability with MySQL in general, and actually that really applies to a lot of other systems as well. One very kind of basic way you can provide high availability is to have a cold standby. For example, with either something like Linux ZRBD, or maybe you have some centralized storage right, which you can use to provide high-availability for. Now, there is also solutions with failover, such as like a master-slave, right? Your master doesn't feel well anymore, right? You fail over to a slave, promoting that to a master, right? Or there are a number of also active solutions which exist out there, such as PXE and group replication. Now, as you are choosing what kind of high-availability solution is right for you, it are good to ask yourself a few questions in this case, right, about the high-availability. The first one is, what really failure modes do you consider, right, and which of them are more likely and more important for you? Because when you often think about high-availability, right, you may be thinking like, oh, you know what, it's either available or not, right, kind of like this black and white. In reality, different problems can happen with the systems, right? Like simple one, say, crash of a server or hardware failure, right? Now you can have things like software bugs, which, for example, can cause storage corruption, which is a different animal altogether, right? Because if I have a storage level corruption, then solutions like DRVD are not going to help me, right? Because if MySQL wrote some crap to the storage, it's going to be replicated with storage replication or persistent highly available storage, right? Network failure, that is whole another story, right? Because there could be so many different network failures ranging from you know, like a single network failure to some partitioning or some asymmetrical and more complicated failures. I remember one interesting failure case was discussed by one of the guys in Google when they have some sort of like misconfigured switch which would be killing off a jumper Ethernet frames, right? And what I was causing for them was two nodes would essentially be able to ping each other, right, from a high availability kind of thing, but then you would try to actually replicate the actual data, which would become in the large volumes they couldn't, right? Crazy, right? I mean, there could be a lot of those very strange network failures on the tail end, right? Like rather rare but important. Now, in many cases, we have to deal with full data center failure, right? Or maybe not, right? Is it possible for the whole data center to go down, and is your application expected to be available even in this case? In some cases, yes. In some cases, you know what, that happens very rarely, right? And they maybe just, you know, wait until it comes back. And then the other very important one is, besides all of those kind of a normal hardware and a software things, there are also such nasty things as people, right? And I think we all agree people are nasty. They take their dirty hands and they do nasty things with them, right? Like logging in and dropping the database, you know, on a production server instead of developer, right? Or writing the queries which are, you know, not really scaling, right? So those things happen, and those can be increasingly more common cause of failures, right, than your hardware failures, as those things can be getting more reliable. And then there are, of course, some of the security issues you also can be thinking about, right? Like you can get, of course, we can have all the set of problems, somebody stealing your data, right, and publishing that on the internet, and there is no high availability can save you against that. But on the other hand, you can have somebody using, let's say, SQL injection, right, to trash some of your data, and that is potentially can be thought through the high availability framework. Okay, another question: what data am I allowed to lose, right? And of course, the first kind of a classical desire, and hey, I never ever want to lose any data. And while that is a very admirable desire, it's also very expensive. And I would say for MySQL environments, a lot of folks really dependent on master-slave replication for years, which is asynchronous, right? And it does not guarantee what you're not going to lose the data. But the amount of also data loss, right, would be typically just few last transactions which couldn't be replicated, right? And in many cases, it is acceptable, right? I mean, for a lot of those kind of the social media environments, right? Well, if one of those cat posts ever get lost, I mean, I would argue that we're doing a positive thing to the world, right? If we are allowing such things to happen. Well, that's just me. Another thing, of course, you may want to desire no data loss for committed transactions, and I think that is a pretty normal. I also see a number of people saying, hey, you know what? Because our developers don't understand transactions and then prefer not to handle error situation, we want to make sure. What? Oh, okay, yes. I guess somebody else sees those kind of developers. That's good. That's good. So, but some people also do not want to make sure their transactions in flight are not lost, right? That means I have open connection which did a couple of updates, right, and haven't committed transaction. Database, crashes. We still want that to kind of continue with no interruptions, right? And that is like a very hard thing to achieve, if you will. And finally, you have to be asking yourself, how quickly do you need to recover, right? And often that has to be mapped also to different failure modes. In many cases, you can say, hey, you know what? If I'm having an active cluster, then I will pretty much want like immediate recovery within a second, right? If that's if one of the nodes crashes. And of course, nothing is really immediate, and by immediate, I mean in this case is what, even if it crashes, my users are not notice any interruption, right? For them, boom, right? The node crashes, but they just maybe have some semi-invisible delay, right? For them, it's web page took a little bit longer to load, but they didn't really notice that as a downtime at all, right? Now, in many cases, you would have let's say full data center failure may take longer to recover as acceptable, because in many cases for DR cases we don't want to maintain, for example, completely full spinning environment somewhere else, which is kind of expensive. Now I think what is very important also is to understand speed of light, right? And the thing is, what things don't go instant, for example, between Europe and America, right? Even if you would want them to. And often you have to understand what we pretty much have between kind of two choices, right, for data propagation. That either kind of gets synchronous, right, then we say, hey, we are waiting for stuff to be replicated, for example, from US to Europe, right, and we wait for that to be there, so we're sure if something happens to, the place in US, it's not getting lost, right? Or we can have an asynchronous, and in this case, well, data gets naturally queued, right? And if that's, let's say, whole data center load goes down, then a data loss can be occurred, right? And in grand scheme of things, we have to choose between those two as a part of our architecture. Okay, now scalability. For scalability, we pretty much have three things which you have to deal with. We have to either scale reads, scale writes, or scale data size. And in many cases, as our application grows, we have to do all of those at the same time, right? And that is where we have to go to much more complicated systems with a single instance. Now, let's look at data distribution and what I mean by that. Now, in many cases, we cannot just keep the data in one place if we are developing their international application, right? And that can come from the two reasons. One is user latency, right? If you want to have a really application which goes very quickly, right? It may be expensive to go from, I don't know, say, mobile network in Vietnam, right, to a data center in America, right? So we may want to get the data closer to user for latency reasons. And then there is also legal and compliance reasons. There are a number of countries which require you to, for example, to keep data related to their citizen, right, in their national borders, right, or have some other regulations, which you may have to deal with, not from a kind of database design standpoint, but from a legal compliance and whatever reasons. Okay, let's jump through to MySQL and go to maybe the same things in a little bit more MySQL specific and detailed way. So when we speak about MySQL, it is good to understand or go through those concepts. So what is a replication, right? So when you speak about replication, we have multiple copies of data, right, which are being updated with changes, right? That is how replication is different from, for example, backup, which is also a copy of your data, but it's offline and it's kind of not tends to be updated, right? Now, replication is obviously, as we spoke, is connected to providing high availability in many cases, right? And if you look at the high availability from a grand scheme of things, we want for our servers, our ability to kind of respond queries, provide user stays up, even if one of the components fails. Now, availability generally is provided through redundancy, right? You would have more than one system, so if one of them fails, something else is going to take the load. And that works increasingly well for the stateless systems, right? It's like you think all this, I would say like a Kubernetes concept, saying, hey, you know what, just keep maintaining 5 copies of my web server, right, and everything will be fine, right? If it is stateless, then I can essentially, you know, kill them at will, add them at will, it all works fine, right? But the databases can't be stateless, because databases is exactly the, you know, the definition of a state itself, right? And that means something else is needed, and we also need not just a redundant computing resource, right, or application server, but we also need the replicated data, right? Multiple copies of data to provide that redundancy, because by definition, single copy of data, right, it's not redundant. Now, replication can happen on different levels, right? It can be on the storage level, right, on the database level, and even on the application level, if you will. Now, if you speak about storage level replication, that is what we mentioned, like your SAN NAS can provide that DRBD. If you're if you're using any kind of cloud storage like an EVS, it also really has redundancy built in through some form of internal storage level replication. Now, a lot of storage level replication tends us to provide just a cold standby, right? Because the MySQL, unlike let's say some other systems, it's not designed to operate on a shared storage. The system, MySQL in a DB, assumes that it has like a monopoly access to the storage, right? And if somebody else changes something underneath it, well, it won't work, right? Now, one wonderful thing about the storage level replication, of course, it's very simple, and that works for pretty much any systems, right? Any system which stores data on disk can be managed this way. Whether we take a MySQL, Postgres, right, or even, you know, like a NFS, you can provide availability through cold standby for storage level replication. Okay. Now, I also want to point out some special example here. Some of you may have heard about the Amazon and Amazon Aurora, right, which also does storage level replication, but that's kind of designed a very kind of different way. And in that stuff, I would more classify that as a database level replication, right? Because that storage is kind of very pretty much is a part of a database technology in the architecture. Now, if you look at the database level replication, that is pretty much most flexible, most common replication, right? And that can provide us hot spare or active environment in some cases. Now, another way is the application level replication, right? I've seen so many people saying, hey, you know what? Database replication is just so hard to set up. Why don't I just go and connect to 2 nodes at the same time, right, and just will update here and there, right? And hey, that works on my laptop, so that means it probably is going to work in real life as well. Now, the thing is, with application level environment, it is very hard to do right. Right, and frankly, over the last few years, I see less of people attempting to do that. Right, so that is Good. Now, in some cases, I would say it is still it's still possible to do that, right? And it's I would say either even reasonable to do that. For example, if you have some some complicated needs for conflict resolution, right? Or you have some other needs where you want to replicate the data across different databases, right? So, for example, we see a lot of environments right now where somebody say, hey, we would use something like Kafka as our data bus, right? And instead of relying on the MySQL, we would make sure what all the data kind of getting written to the Kafka, right? And then we can have a MySQL, right? And maybe some other Hadoop, right? Or whatever as a consumers of that data flow, right? For their needs. So, you can also think about that as some kind of a user-created replication, right? But that is not your kind of classical stupid replication connected to two database nodes, right? And try to write the same data at the same time. Okay. Sharding. Now, when you look at the large-scale databases, we tend to find what data is way too large to fit at a single database or even single replication tree, right? So what that means is that we split the data by certain criteria and put that in a separate kind of chunks called shards, right? And we put them on a separate clusters, right? Now, typically we shard one of those two ways, right? If you think about somebody like Facebook, they often would shard by user, right? That means, hey, we map users to those shards, right? And then all the data to the user, right? Or some of the data by the user will be placed in that shard. In other cases, a lot of software as a service companies, they shard by customer account. Companies also referred to as tenants, right? Then I would often have a lot of people which belong to the same tenant, same organization. They have a data which is tightly coupled together, but different organizations are completely separate, right? Think about something like, I don't know, a Slack, right, or Salesforce. In those cases, those different organizations are pretty much separated from each other for normal operational purposes. Now, sharding is almost always used as some kind of a replication. And why is that? Well, because as you scale, there is a higher and higher probability of something, of a failure to happen, right? So, for example, if I have just one MySQL master server, and I have a mean time between failures 3 years, right? It may be completely acceptable, right, not to have a lot of replication. Maybe just have a backup. Well, it crashes once or 3 years. Maybe I have a little bit of downtime. Not a big deal. Now, if you have 100 of them, that will mean the average time between their crashes, right, would be about 3 days. Well, which is probably less so, right? That is why when we have a massive sharding, then we tend to have some sort of a replication with that built in. Now, the next thing that I mentioned important is the failover management. Now, what does that mean? If you look at the many replication modes, such as MySQL classical replication, it doesn't have any mechanics to handle failover on its own. It needs help, right? What would MySQL do if you have, let's say, master and 2 slaves, and the master crashes? MySQL will do nothing, right? 2 slaves will sit out there and say, hey, you know what? It's kind of, I can't connect to the master. Let me just, wait and sit and wait and do something, right? You actually need some other process to say, okay, now I want to promote one of you remaining slaves to the master, right? And do whatever environment changes needed to complete that that process, right? And then 2 things have to happen out there. Somebody needs to decide how to do that failover. I have 2 masters, 2 slaves, 1 master. I have to figure out, oh, this slave is kind of ahead, so I need to may elect him as a master, right? Or maybe have some other solutions, right, to perform. And then also to perform a failover, right? Saying, oh, now I need to reconfigure that slave as a master. And I separate those two because there have been some tools existed which would say, hey, you know what? We only do automation of perform a failover, but we want you as an individual to decide when to do that failover, right? Because we don't want, for example, to perform a failover when it shouldn't happen, right? For example, when you just overloaded master with some, nasty queries, and guess what? If you simply fail over to the slave, well, it will be overloaded with the same queries again, right? Now the other thing is the traffic management question, right? And there are multiple functions which can be performed by those proxies, load balancers, right? You name them. Scaling large number of connections, routing traffic to the right shard if that's their role. Maybe read-write splitting, right? So we can actually not do it in application, but let them decide which traffic to send to the slave and which not. Maybe some sort of load management, right? So if we have one of the servers overload to move traffic from it, as well as things like avoiding dead nodes, right? Maybe if I have multiple slaves, one of them crashed, I don't want to be sending traffic to that, right? Even until it's kind of completely removed from configuration. So what do we have in terms of options in MySQL, and what are their properties? First one is would be our classical MySQL replication, group replication, Galera and Percona XtraDB cluster, as well as MySQL and DB cluster, right? These are the most common things which you can use. Classical MySQL replication is pretty much this. You have master, slave, binary logs are being written to the master, and they are consumed by the slave in a synchronous fashion. Each of them has their own copy of a database, right? So it's pretty independent. So what are properties of MySQL replication? By default, MySQL replication is asynchronous. So there is absolutely no guarantee how far the slaves are compared to the master. You can also consider that to be semi-synchronous, right? But remember, semi-synchronous is actually asynchronous, right? Semi doesn't mean it's kind of just as good as synchronous, right? So what semi-synchronous does, it says, hey, that means I will commit on my master, right, here, when the data event made it to the relay log, right, on the slave, but not necessarily applied, right? So if semi-synchronous replication, you are sure now if master crashes, the data will make it to the slave eventually, right? Eventually, right? So it gives us kind of eventually consistency of a sort, right? But it's not synchronously applied to the slave in this case. It can be parallel, and what I mean by that is, if some of you remember or know MySQL from the early days, replication was single thread, and that was very limited in its performance. That's not the case anymore since MySQL 5.7. You can also have now multiple masters for a single slave, called like multi-source replication, again since MySQL 5.7. And two big limitations remain for MySQL replication. Is A, there is no conflict resolution or sort of protection of any time, right? If you do any kind, if you set up a replication and if you happen to write some conflicting data on the slave, well, you'll just have replication, master and slave data inconsistent, right? And maybe replication will stop due to conflict at some point, right? But there is no specific protection out there. And then there is also no built-in failover, right? I mean, it's still, by default, replication will simply stop if master isn't available. Now, MySQL replication, which has kind of its own simplicity, it allows us to create many different topologies, right? Which are kind of as a few examples here. We can have few masters which are streaming to a single slave, right? For example, to consolidate the data, right? We can have the ring replication set up. You probably don't want to, but that's kind of in theory possible. You can have a multi-level slaves. If you want, there are some slaves connected to each of the slaves. And what is also important, you don't have to replicate everything in MySQL replication. You can say, hey, I have a two-level slaves where I replicate everything from here to there, and then only replicate some of the data here, right, for example. So MySQL replication is, with its whole simplicity, it kind of allows for good and bad to create very flexible, weird MySQL replication hierarchies. That is the example. I want to just put a shameless plug here with our PMM, Percona Motion Management. We have some nice dashboards for replication among other things. Okay, moving on to MySQL group replication. MySQL group replication kind of works in a little bit different way, right? In this case, we have a group of nodes, right? We just call it replication group, and you can see from conceptual standpoint, they are all masters, they are all peers, right? What are the properties of this replication? We can write either to any of the nodes, or actually by default, it configures itself so there is one node is elected as writer, right, and the other nodes are read-only, they're intended to be only read from, right, and that's done because that gives you kind of more, comparability with a standard replication, if you like. This is also like asynchronous replication with flow control. What does that mean? Well, that means that the data is still asynchronously replicated, but we have a flow control. That means we don't really allow slaves to be lagging by unlimited period of time. There is like this elastic robot there, right? And if a slave becomes too far behind, it's say, hey, master, hold off, please. I am not able to keep up. Can you please slow down a little bit, right? We also have conflicts which are being prevented, in this case, through synchronous certification, right? While changes are not actually being applied synchronously, they are certified, right? And that means they are guaranteed to be committed to the cluster synchronously, which allows us to avoid conflicts. It has an automated failover, and what that means, or built-in failover. So what that means, if one of the nodes crashes, right, then it just kind of leaves the cluster. If that node happens to be that dedicated writer, then other node gets elected, and so on and so forth, right? So a lot of good stuff was there. There is a still limitation, though, that there is no automated provisioning. And what I mean by that is if you want to set up a node for MySQL group replication, you need to get your data from somewhere, like maybe restore from backup, manually, same as you do for standard replication. Okay. The next piece is Percona XtraDB cluster and Galera, right, in this case. Now, the idea in this case is very similar, right? If you look at in this case, there is a group communication. There are multiple nodes which belong to the group, right? And reality here is what, from many properties, Galera and MySQL group replication are similar. The frank reality is what Galera and PXE was around for a long time, right, since MySQL, times of MySQL 5.5. And I think folks in Oracle seeing how useful this kind of replication is, implemented group replication, right? And in this case, it's kind of by design, it shares many many similar properties. So we have a write to any nodes. It's a certification-based replication the same way. Now, in this case, it's also asynchronous kind of replication of synchronous certification, but there is an option you can ensure there are no stale reads, right? You can instruct the cluster saying, hey, you know what, please hold off select the execution until the data actually propagated completely to this node, right? So that is a mode in this case which is available. There is a built-in failure and also built-in node provision, right? So in this case, Percona XtraDB cluster behaves more modern, right? If you take the, I don't know, let's say freshly installed node, right, or put up, I don't know, let's say Docker container and say, hey, can you please join the cluster? It will automatically perform everything which is needed to join, like copy the data and so on and so forth, which is useful. Now, maybe I should explain a little bit how the transaction control works in PXE. And that image is for PXE and uses its terminology, but really the MySQL group replication concepts are very similar in this regard. So if you speak about the user transactions, all the updates, right, during that transaction are performed completely locally, right? There is no network communication when you are running updates of any kind. You simply have something which is accumulated, which is called write set. This is pretty much, you can think about as a set of primary key values, right, which are going to be updated. Then, when you trigger the commit, then event is sent to other nodes, right? And that is what's called the certification, and that is pretty much the only network communication which is required, like one commit per one round trip per commit, right? And then in this case, certification happens, right? In this case, through that group communication, and then you would have a physical commit or rollback based on certification results. Now, a good thing to understand is another node, which is in this case slave, and note the slave for a purpose of a transaction, right? Different transactions may have a different master and slave, right? In this content, the certification will get that event queued, and then apply threads or threads which will apply those events locally, right? So it is possible for some glitch, right, to happen, for some lag to happen in this case. Now, what is also interesting is you can see from this diagram is while it is most likely what your master for the purpose of transaction will commit transaction first, it is also possible for slave for the purpose of this transaction to commit it first, right? So, for example, if we just get a stall on a disk I/O on this kind of final commit operation, then this guy can commit the transaction faster, right? Now, you will ask, okay, but what happens if you commit the transaction, let's say here, and this cannot commit a transaction because, let's say you had like some disk I/O error in this case. The concept here is what the node which fails to commit the certified transactions must commit suicide, right? Like, or pretty much crash, exit the cluster, right? Wherever you want it. But I like commit suicide. I think there is some word of finality to that, right? Okay. So we also have in PXE number of performance improvements we did recently, and we are really very proud of the dramatically increased concurrency, which really could be up to 10 times for write-intensive benchmarks for variety of workloads. So that is good, and I should thank folks at Oracle, right, for creating a competition out there. So now we can, compete in our benchmarking, right? In terms of which of solutions is actually faster. As you can imagine, in our Percona monitoring management tool, we also have some nice dashboards to visualize Percona XtraDB cluster, or actually any other Galera solution, right? Galera for MySQL, MariaDB, and so on and so forth. Okay, MySQL cluster. Okay, now let me do a poll here. Anybody is using MySQL cluster as MySQL NDB cluster here? Okay, anybody used MySQL cluster in the past? Okay. Okay, so anybody tried using MySQL cluster in the past? Okay, well, that is, I think, the main point, right? I feel like I do include this technology out there, but very few people actually use it, because while I think it will have a lot of conceptual ideas, it's really achieved only niche adoption so far. And this is a solution which is has a lot of nice features, such as kind of automatic sharding, right, and distributed query execution, but it also has a lot of limitations that use a different storage engine and so on and so forth. Well, okay. Now let's talk quickly about sharding in MySQL. Sharding in MySQL is typically either painful or very painful, right? So I mean, there is no such things as, like, oh, easy sharding MySQL, right? Not in MySQL. There are no built-in or standard solution out there, right? Frankly, if you look at a lot of the early MySQL adopters, like folks at Facebook, they really have some custom application level sharding which they implement, right? And they're happily use it. Now, when you think about sharding, I think it's good to think about a few things which are important. The most basic thing with sharding is a query route, right? Like, I route my queries to the right shard. And that is relatively easy, right? And frankly, that is how many people jump into, oh, I'll just do it on the application. It's okay. More complicated is, okay, how are you doing data aggregation for cross-shard queries if you need them? That is much more painful, especially if you want to implement that in the application, right? And it's hard to do right. And the third one is shard balance, the operation handle of things, right? Let's say you have a shard cluster 5 shards, you want to add 6. How exactly are you going to do that, right? That is not easy, right? So maybe one of your 5 shards became overloaded for some reason, because maybe they became over large account on it. How do we balance that shard, moving that traffic somewhere else? All of those things are very important, right, for sharding, but it is hard to get right. So what kind of solutions exist for sharding out there in the community? I would say by far the most advanced right now is Vitesse. That is something which started by team at Google YouTube, and that's now open source, and it's available from a cloud native computing foundation. It's outside of YouTube. It was also deployed in Slack, right? Which is good, right? Because when technology starts to is only developed in one organization, it's often kind of really only designed to solve a problem for that organization, right? The fact somebody else could deploy and scale gives much more confidence. It now supports MySQL protocols and many of MySQL features. Not all of them, right? But for a lot of applications, you can just connect it to Vitesse, and it will automatically manage your query, including doing the multi-shard data aggregation when needed. And it supports those cross-shard queries and supports resharding, right? So that's a solution we check all the checkboxes. Here is an example of architecture, right, of Vitesse, where you can see there's, let's say, some management comments. There are, some metadata for topology, right, how exactly it turns data. There is, let's say, some little server, right, for each of the shards, which kind of manages it, and there's mitigate, that is your, you can think about like some of the proxy, right, to take all queries and manage them as failover. For failover in MySQL, the classical MySQL application, both main one of the and these are just the most popular ones where I find more kind of everything that is very around right? But the problem is you are adding one more network hop, right? So that is going to impact performance somewhere. The other way to deploy proxy SQL is when you deploy proxy SQL on the application server side. You think about proxy SQL as part of a client library in a sense, right? And then each of those instances, right, can route connections appropriately, perform, failover and so on. Now, in the modern proxy SQL, there is you can make proxy SQL instances essentially to replicate between each other, so they can have a configuration changes applied to them at the same time, right? So if they know what this node goes down, right, then this information will be kind of instantly propagated to all of them. Now, this works if you don't have too many application servers, right, of course. I mean, if you have, I know, let's say 10,000 application servers, then that's going to become maybe too complicated to maintain. Now, with proxy SQL, of course, again, we have a nice dashboard for that, right? Let's yet another shameless plug, but that's okay because PMM is open source, right? And let's make it okay, I guess. Right? Now, I also want to mention to you cloud-only options. Now, we see a lot of people are deploying database as a service in a cloud because that really allows to save a lot of sort of, like rudimentary pain, right, taking backups and so on and so forth. And that is also provides typically its own built-in availability functions, right? Like wherever Amazon JS, Aurora, Google Cloud SQL, Azure Database for MySQL, all the big clouds, they do have some database as a server options with some built-in availability options, right, which you can consider. None of them, at this point, as I know, have some sort of built-in sharding support, right? So sharding, if you need that, is still going to be on you. Okay. Now, let's go beyond MySQL. Now, MySQL is hopefully an important part of your data infrastructure for years to come. But the thing to know about MySQL is while MySQL is good for many things, MySQL is not good for everything. Right? That is, there is no silver bullets in technology. And then we often see MySQL being used with other technologies out there, right? Maybe we have Redis and Memcache used for caching, right? Or we use like Elastic or Solo used for search, right, in this case. Or I mentioned Kafka already, right? If you want to kind of some queue or streaming data, Kafka is great, right? Or maybe you would use like Hadoop, ClickHouse, Spark, right? Many other technologies if you want to say have some large-scale analytics, because you know what, single thread query execution kind of just not cutting it anymore, right? So in this case, we have to deal with a cross-technology application, and there are multiple solutions here as well. We have some trigger-based replication tools, which kind of really exist for all the databases. I have seen people just doing that as a self-made way, right? Like, hey, I just set up the triggers, right, and maybe some UDFs and write the data somewhere. As well as for solutions like Symmetric DS exist to do that. We have a lot of Kafka gateways to MySQL, right, which would essentially typically read MySQL binary log and put the data to Kafka, such as Debezium, right, or Yelp has open source MySQL Streamer. There are actually more of those solutions, both open source and closed source ones. Tungsten Replicator, that is another technology which can replicate from MySQL to a variety of data store, right? Or actually also it can replicate, for example, from Oracle to MySQL and so on and so forth. And then we also see a number of folks have been deploying their custom MySQL binary log consumers, right? There is, for example, Tarantul and ClickHouse, they implemented their own tools, right, to consume binary log and replicate it to their technology. Like a wonderful thing in this case is a lot of that stuff is open source, right? So if you want to write your own tools, let's say, hey, I want to consume binary log, there are tools in Go, Python, C, right, Java, language of your choice, you would be very easy to be able to find that. Okay, so if you look at as a summary, in this case, we can see that there are a lot of options exist for building distributed architectures with MySQL. I would say perhaps there are too many, right? I mean, in many cases, I wish there would be fewer options, but they would work better, right, or support better. And I think what it also makes MySQL very exciting is that there are also lots of options integrating MySQL with other open source data stores, right? So we can really build a very effective multi-data store environment, right, where you get a different benefits for that. Now, if you are interested about the open source databases, to learn more about open source databases, I would like to welcome us to our conference, Percona Live, which takes place not last month. It was weird, right, to invite somebody to last month's conference. Next month, right, in April in Santa Clara. It's going to be wonderful. There's a lot of talks about a lot of technologies from many famous companies. So with that, thank you, and I would be happy to answer questions.
If you have a question, just raise your hand.
Any questions? Yeah.
What would you recommend most for like sort of intra-continent replication where you have fairly frequent internet general 10 to 30 second interrupts?
Yeah, well, so if you have this intercontinent, right, in this case, then often you would be limited to the asynchronous replication. That's like the typical solution you would have. Now, I would say, as I mentioned, unfortunately, built-in MySQL replication doesn't have any good conflict resolution built in at this point, right? But I am hopeful what your concerns and concerns of many others would be heard, and in some of the future versions, that will be resolved.
Okay. You joked earlier a little bit about the Galera nodes committing suicide, and we saw that a lot.
Okay. You saw what a lot?
The Galera nodes committing suicide. We had Galera cross the ocean, and it would have like a 30-second hiccup, and then both sides are like, I'm down.
Yeah. Well, I would say you're right. Now let me state something important right, to what you stated, right? So if you have their Galera or MySQL group replication, right, those technologies, they typically look to solve a network partitioning problem, right, which is solved through a quorum, right? And that doesn't work with two nodes. Because if you have two nodes, right, or 2 and 2, right, let's say 4 nodes, and you break in between, then it kind of sucks, right? You don't get, more than 50% votes anywhere, and both nodes crash, right? So if you have environment like yours, you want to make sure you have either 3 data centers, or if that's expensive, you only need 2, then also put things like Galera Orbiter in a 3rd data center, right?
What's Galera Orbiter?
Oh, Galera Orbiter, that is the very lightweight node, which essentially does not store any data, but it's a tiebreaker, right? So in this case, if you have 2 data centers, network within them fails, right? Or let's say one of them loses connections to the rest of the world, then Galera Orbiter will decide which of those 2 has actually have connection, right? And to the world, and which just became isolated.
Okay. Yeah, we essentially did the same thing. We had like 4 hosts in one data center and 3 in the other, so we always knew which data center was going to commit suicide. And luckily our data set was really small, so we just restreamed the data center.
What's that?
We would have 4 nodes in one data center, 3 in the other. And then
so that's right. I mean, if you have a 3 and 4, then that would work. Of course, if a data center 4 dies, then the other one will crash as well, right? Because of we'll see it in isolation. Okay. Good. Any other questions? Okay, well, no more questions. That means I did either extremely good or extremely bad. I leave you to judge that. Anyway, thank you.
Thank you, Peter. How much?
Thank you.
Very insightful.
Okay.
Very insightful. A lot of info on
Okay.
like XtraDB.
Okay. Good to hear.
harder to get to.
Test mic. Oh, I struggle with that one.
Yeah, and
But,
so you just put your thumb like this, and then just kind of
got it.
move it.
Okay, cool.
So,
Yeah,
turn it off.
I learned that the hard way. Test. Test mic, test mic, test. Hey, thank you for coming to Scale 16.